Hello, everybody, and welcome to today's class. Today, we are going to go into topic 2.2, which is an introduction to functions. So let's start. So for this subtopic, we have the following 4 points. Zero, we're gonna have a little background. Number one, we're gonna define what a function is. Number two, we're gonna speak about its terminology and notation. And number three, we will have a little activity about what evaluation of functions means. So first, the background. In this background, what I want to tell you is the graphical representation of a set and its elements. So in here, what I'm giving you is four sets. This set or this diagram represents the set of the natural numbers. This diagram represents the set of the letters of the Latin alphabet. This set represents the regular polygons, and this set represents the colors. So this is a very typical representation of sets, and its elements are represented by points. For example, in the first set, I'm exemplifying the element number one because it's part of the natural numbers, right? The number two, the number three, the number 11. I could go on forever and I could draw many more points, the number 4, the number 100, etc. But only sometimes for the purposes of these diagrams, only a few of them are necessary to write. For example, here, the regular polygons, I'm giving you three examples: the square, the equilateral triangle, and the regular hexagon. But I can draw more and more regular polygons, for example, the pentagon and so on. So this is a very typical representation for sets and the way to represent its elements as points inside these enclosures. So let's go to point number one. What is a function? Okay, there are two main ideas that describe the idea of a function. The idea one is the idea of a function as a machine. You will understand what I mean in a moment. And the idea two is the requirement of only one output for each input. So these two ideas you will understand in a moment. Just memorize that there are two basic ideas that describe the idea of a function. Okay, and that is the idea of being a machine, kind of, and the requirement of only one output. Just memorize these two things, okay? So the idea number one, the idea of function as a machine. Let's understand what this means. Okay, I'm gonna draw the following diagram, and I want you to understand that what this means is some sort of machine, okay? I'm gonna call this machine F. And these two little things in here are something like places to place an input and a place that outputs something, okay? Because that's what machines do, right? Machines take some input, some material, and then they do some processing on the input, and then they give you some output. Okay, so let's see what this means. Suppose that we have this machine F, and suppose that we input the number 1. Then the machine does some processing on the input, on the number 1, and it outputs the number 2. Okay? 1 goes in, some process takes place, and then the machine outputs the number 2. That's what the machine is doing. Okay, I'm going to represent that also in this way. I'm going to draw this set, in this set, and this point, which is the number 1, and this point in here, which is the number 2. And what F is doing, what this machine F is doing, is taking this point or this element of this set as an input, and it's transforming it into this output. Okay, input and output, and the machine F is simply transforming this input into this output. Another example. Suppose that you give the machine the number 2 and it outputs the number 4. I'm going to represent that in here. So this point, this element of this set of numbers, the number 2, is being taken by the function, and the function produces the output 4. So you give this input to the function, and the function produces this output. So basically, the function is associating this output to this input. Let's do one more. Suppose that you give the function the number 3, goes in, some process takes place, and it gives out the number 6. So 3 is being taken by the function, by the machine F, and it gives as an output the number 6. So 3 is being matched to the number 6, or this output is being associated to this input. Okay, so what do you think this machine is doing? Pay attention to what's happening. The number 1 goes to number 2, the number 2 goes to number 4, the number 3 goes to number 6. So I think by now you understand what this machine is actually doing. What this machine is doing is this. It takes a number x as an input, and it gives out the number 2x as the output. Okay, that's what this machine is doing, right? This machine is the machine that doubles the input. That's what it does. Okay, let's go on into the next example. Now suppose I give you this other machine. I'm gonna call this machine G, and again it has a place for an input and a place for the output. And let's see what this machine does. I'm gonna give it the number 1 as an input, and the machine takes it and it outputs the number 1. So the machine is taking this number, the number 1, and is transforming it into the number 1. Now the machine takes the number 2 and it outputs the number 4. So the number 2 is being taken by the machine G, and it outputs the number 4. Next example, we give it the number 3. The number 3 goes in as an input. The machine G reads it, transforms it somehow by some process, and it outputs the number 9, which we can represent in this way. Okay, so this is what the machine G is doing to any number. Okay, what do you think this machine is doing? How can we express it in general terms? What this machine G is doing is taking a number as an input, and it gives out as output the number x squared. So this machine, in general terms, takes a number, it does some process on the number, which in this case is squaring it, and it gives out the result. You get it? Okay. Now, this type of machines that we're talking about don't necessarily have to talk about numbers or have to receive numbers as inputs and give them as outputs. For example, I can create this other machine. I'm gonna call it machine H. Again, this is the input, this is the output, and look at what I'm gonna do next. I'm gonna give this machine letters of the alphabet. Okay, for example, I'm gonna give it the letter A. The machine takes it, does some processing on this input, and it gives you the number 1. So I'm gonna draw here 2 sets, and this set is gonna be the set of letters of the alphabet. So what this machine H is doing is taking this letter, letter A, and associating to an output of 1. Now, if you give it the letter B, it outputs the number 2. So I think by now, you know what this machine is doing. But just one more example. It takes the letter E as input, it does some processing on E, and as output, it gives you the number 5. So this machine H is taking this letter of this set and is transforming it into an output 5. Okay, so what is this machine doing? This machine receives letters, which are not numbers, right? And what this machine is doing is it's giving you its order in the alphabet, right? A is the first letter, B is the second letter, E is the fifth letter. So H is taking a letter of the alphabet, okay, that's what this X stands for, and it's giving you as output the order of such a letter in the alphabet. That's what this machine is doing, okay? So these machines not only take numbers as inputs or as outputs, they can take whatever, it doesn't matter. Okay, so what am I talking about this? About machines transforming inputs into outputs. Okay, because one of the most common conceptions about functions is that functions are in fact machines that take some inputs. They make some operations on the inputs or some transformations, some operations or something, and then they give you an output. Okay, just like this. That's one of the basic conceptions about functions. So we can call a machine a function, and we could call this machine function H. Okay, so that was the first idea, the idea of function as a machine. Now let's go to the second idea. We need that these machines have only one output for every input. I repeat, only one output for every input. Why do I say this? Okay, because I could create machines such that they give you 2 outputs or more for every possible input. For example, I'm gonna create this machine. Look, I'm gonna create the machine T. I'm gonna call this machine T, and I'm gonna program this machine so that it takes as inputs numbers, and as output, this machine is gonna give you the square root of the input. Okay, so let's see how this machine works. So I'm gonna give it the number 4 as input, and then the machine takes it in, it calculates the square root of 4, and it gives you the outputs. Okay, so it's gonna give you 2 outputs. It's gonna give you 2 because 2 is the square root of 4, because 2 times 2 is 4. Did it also, it's gonna give you the number -2 because -2 times -2 is also 4. So this machine T is taking the number 4 into 2 different outputs, 2 but also -2. Okay, another example. Let's give this machine the number 9. It takes it in, it calculates the square root of 9, and it's gonna give you as results 3 and -3. So the number 9, the element 9, is being transformed into the number 3 but also the number -3. Okay, so that's what this machine is doing. And if a machine of this type takes an input, a single input like 4, And as outputs, it gives you one and more possibility. For example, in this case, it gives you two outputs. For every single input, it gives you two outputs. Then these machines are not functions. Okay, these machines are not functions because they are violating this principle. For a machine to be a function, they have to have only one output for every input. Only one output for every input. Let me give you another example of a machine that could give you two outputs for a single input. Let's suppose that this machine, which I'm going to call machine Z, takes an input, a number, any number, and as output is going to give you its antecessor and its successor. For example, if I give this machine the number 3, it's going to give me the number 2 because that was the antecessor of 3, and it's also going to give me the number 4, which is the successor of 3. So this machine Z, is taking the number 3, and as outputs is producing the number 2, but also the number 4, and so on. I can give more examples, but I'm going to stop right there. So also this machine, even though it's transforming some input into some output, it does so by assigning two possible outputs for a single input, and that disqualifies this machine to be a function, okay, because it's giving more than two outputs, more than one output, in this case two, for a single input. So those are the two main ideas behind the concept of function. So now let's go into a non-formal definition of function. What I want you to understand about this definition is that it is not the most mathematical or the most precise definition, but that is okay. If you actually look up the definition of function, you will find that there are many definitions, each one with increasing degrees of formality or preciseness, okay? This is a good definition for high school. So let's see. What is a function? A function is this. Let's read. A function is a process or a rule that associates each element of a set called the domain with only one element of another set called the codomain. In Spanish, these words are pronounced dominio y codominio. Domain and codomain. And here a little remark. These two sets, the domain and the codomain, could actually be the same set. So for example, let's look at these two diagrams. In here, I'm representing a machine or a process F that is taking elements of this set, which is the set of real numbers. Look here. And it's also called the domain. This is the domain of this function, okay? And it's taking the number 1 and it's transforming it into the number 4. So this machine or this function F is associating the number 4 as output to the number 1 as input. And also it's associating the number 8 as output for the input of 2, and so on, okay? So if you can see, it's associating only one element, okay, for every single input. So this checks. This is a function because it fulfills or satisfies the requirements given in the definition. Now let me give you a counterexample. Suppose that this is machine G, and machine G is taking elements of this set of real numbers into other elements of this set, which is also the real numbers. Remember, the set of inputs is called the domain, and the set of outputs is called the codomain. But let's see what G is doing, and let's see why I'm saying that G is not a function. Okay, so G takes the number 1, the input 1, and it associates it to the output 3. So it's taking the number 1 and it transforms it into the number 3. Okay, that's fine. That's perfectly cool. But the problem lays right here with the number 2. G is taking as input the number 2 but it's producing two outputs for such input. Okay, it's producing the number 4 and the number 5. So G is associating to this element of the domain two possible elements of the codomain. And with just a single violation of the rule, like in this case, okay, with a single violation, that's enough to disqualify G as a function. Because you may be thinking, well, G respects the requirement for this one, right, for this element, because it's associating the number 1 to only one element of the codomain, and it's associating the number 3 of the domain with only one element of the codomain, and that's okay. But it violates the principle with the number 2, and only one violation is enough to disqualify G, this machine G, as being a function.